Hello friends, in this lecture we shall be talking about the kinetic theory of gases, one of the main subjects in thermodynamics. A gas consists of atoms either individually or bound together as molecules that fill their container's volume and exert pressure on the container's walls. We can usually assign a temperature to such a contained gas. These three variables associated with a gas, that is, volume, pressure, and temperature, are all a consequence of the motion of the atoms. The volume is a result of the freedom the atoms have to spread throughout the container. The pressure is a result of the collisions of the atoms with the container's walls. And the temperature has to do with the kinetic energy of the atoms. Kinetic theory of gases, the focus of this lecture and a few more, relates the motion of the atoms to the volume, pressure, and temperature of the gas. Applications of the kinetic theory of gases are countless. Automobile engineers are concerned with the combustion of vaporized fuel in the automobile engine. Food engineers are concerned with the production rate of the fermentation gas that causes bread to rise as it bakes. Environmental scientists are concerned with how heat exchanges between the oceans and the atmosphere can affect weather conditions. The kinetic theory of gases relates the macroscopic properties of gases to the microscopic properties of gas molecules. Our goal here is to explain the macroscopic properties of a gas in terms of the behavior of the molecules that make it up. However, there is an immediate problem. Which gas? Should it be hydrogen, oxygen, or methane, or perhaps uranium hexafluoride? They all are different. Experimenters have found, though, that if we confine 1 mole samples of various gases in boxes of identical volume and hold the gases at the same temperature, then their measured pressures are almost the same, and at lower densities, the differences tend to disappear. Further experiments show that at low enough densities, all real gases tend to obey this relation PV is equal to nRT, which is the ideal gas law. Here, P is the absolute pressure, N is the number of moles in the gas, and T is the temperature in kelvins. The symbol R is a constant called the gas constant that has the same value for all gases. Provided the gas density is low, this law holds for any single gas or for any mixture of different gases. We can rewrite equation KT1 in an alternative form in terms of a constant called the Boltzmann constant K, which is defined as K is equal to R upon Na. Substituting the value of R and Na, we can find out its value to be equal to 1.38 into 10 raised power minus 23 joules per Kelvin. This allows us to write R is equal to Kna. Then we know that the number of moles N contained in a sample of any substance is equal to the ratio of the number of molecules N in the sample to the number of molecules Na in 1 mole. That is, N is equal to N upon Na. The three symbols in this equation can easily be confused with one another. So you should sort them with their meanings now before you end in an confusion. Using KT2 equation, we find that Nr is equal to Nk. Substituting this into equation KT1 gives a second expression for the ideal gas law, that is PV is equal to NKT. Here note the difference between the two expressions for the ideal gas law. Equation KT1 involves the number of moles N and KT3 involves the number of molecules N. You may well ask, what is an ideal gas and what is so ideal about it? The answer lies in the simplicity of the law that governs its macroscopic properties. Using this law, we can deduce many properties of the ideal gas in a simple way. Although there is no such thing in nature as a truly ideal gas, all real gases approach the ideal state at low enough densities, that is, under conditions in which their molecules are far enough apart that they do not interact with one another. Thus, the ideal gas concept allows us to gain useful insights into the limiting behavior of real gases. This video here gives a dramatic example of the ideal gas law. A stainless steel tank with a volume of 18 meter cube was filled with steam with a temperature of 110 degrees centigrade through a valve at one end. The steam supply was then turned off and the valve closed so that the steam was trapped inside the tank. Water from a fire hose was then poured onto the tank to rapidly cool it. Within less than a minute, the enormously sturdy tank was crushed, as if some giant invisible creature from a grade B science fiction movie has stepped on it during a rampage. Actually, it was the atmosphere that crushed the tank. As the tank was cooled by the water steam, the steam cooled and much of it condensed, which means that the number N of gas molecules and the temperature T of the gas inside the tank both decreased. Thus, the right side of equation KT3, PV is equal to NKT, decreased, and because volume V was constant, the gas pressure P on the left side also decreased. The gas pressure decreased so much that the external atmospheric pressure was able to crush the tank's steel wall. Work done by an ideal gas at constant temperature. Suppose we put an ideal gas in a piston cylinder arrangement like the one shown here. Suppose also that we allow the gas to expand from an initial volume Vi to a final volume Vf, while we keep the temperature T of the gas constant. Such a process at constant temperature is called an isothermal expansion, and the reverse is called an isothermal compression. On a PV diagram, an isotherm is a curve that connects points that have the same temperature. Thus, it is a graph of pressure versus volume for a gas whose temperature T is held constant. For n moles of an ideal gas, it is a graph of the equation P is equal to nRT into 1 upon V and is equal to a constant into 1 upon V. This figure here shows three isotherms, each corresponding to a different constant value of T. Note that the value of T for the isotherms increases upward to the right. Superimposed on the middle isotherm is a path followed by a gas during an isothermal expansion from state I to state F at a constant temperature of 310 Kelvin. To find the work done by an ideal gas during an isothermal expansion, we start with this equation. W is equal to integral of pdv from Vi to Vf. This is a general expression for the work done during any change in volume of any gas. For an ideal gas, we can use equation KT1 to substitute for P, obtaining W is equal to integral of nRT upon V into dV from Vi to Vf. Because we are considering an isothermal expansion, T is constant, so we can move it in front of the integral sign to write W is equal to nRT into integral of dV upon V from Vi to Vf and is equal to nRT into natural log of V from V1 to Vf. By evaluating the expression in brackets at the limits and then using the relationship natural log of A minus natural log of B is equal to natural log of A upon V, we find that W is equal to nRT into natural log of Vf upon Vi. For an expansion, Vf is greater than Vi. So the ratio Vf upon Vi in this equation is greater than unity. The natural logarithm of a quantity greater than unity is positive, and so the work W done by an ideal gas during an isothermal expansion is positive as we expect. For a compression, Vf is less than Vi, so the ratio of volumes is less than unity. The natural logarithm in that equation, hence the work is negative, again as we expect. Pressure, temperature, and RMS speed. After going through this section of the lecture, you will identify that the pressure on the interior walls of a gas container is due to the molecular collisions with the walls. You will also be able to relate the pressure on a container wall to the momentum of the gas molecules and the time intervals between their collisions with the wall. For the molecules of an ideal gas, we will be able to relate the root mean square speed and average speed. You will also be able to relate the pressure of an ideal gas to the root mean square speed of the molecules. Here is our first kinetic theory problem. Let n moles of an ideal gas be confined in a cubical box of volume V. The walls of the box are held at temperature T. So, what is the connection between the pressure exerted by the gas on the walls and the speed of the molecules? We ignore, for the time being, collisions of the molecules with one another and consider only elastic collisions with the walls. Figure shows a typical gas molecule of mass m and velocity v that is about to collide with the shaded walls. Because we assume that any collision of a molecule with a wall is elastic, when this molecule collides with a shaded wall, the only component of its velocity that is changed is the x component, and that component is reversed. This means that the only change in the particle's momentum is along the x-axis, and that change is delta px is equal to minus mvx minus mvx, and that is equal to minus 2 mvx. The molecule will hit the shaded wall repeatedly. The time delta t between collisions is the time the molecule takes to travel to the opposite wall and back again at speed vx. Thus, delta t is equal to 2L upon Vx, where 2L is a distance. Note that this result holds even if the molecule bounces off any of the other walls along the way, because those walls are parallel to x and so cannot change Vx. Therefore, the average rate at which momentum is delivered to the shaded wall by the single molecule is given by this equation. Delta Px upon delta T is equal to 2mvx upon 2L divided by Vx, which is equal to mv square x divided by L. From Newton's second law, the rate at which momentum is delivered to the wall is the force acting on that wall. To find the total force, we must add up the contributions of all the molecules that strike the wall, allowing for the possibility that they all have different speeds. Dividing the magnitude of the total force by the area of the wall then gives the pressure on that wall. Thus, using the expression for delta Px upon delta T, we can write this pressure as P is equal to Fx upon L square, which is equal to mv square x1 divided by L plus mv square x2 divided by L and so on up to mv square xn divided by L and whole divided by L square, which is equal to m upon L cube into v square x1 plus v square x2 and so on up to v square xn. Here n is the number of molecules in the box. Since n is equal to n into Na, there are n into Na terms in the second set of parentheses in this equation. We can replace that quantity by n Na into v square x average, where v square x average is the average value of the square of the x components of all the molecular speeds. The equation then becomes P is equal to Nm into Na upon L cube into v square x average. However, Mna is the molar mass m of the gas, that is, the mass of 1 mole of the gas. Also, L cube is the volume of the box, so P is equal to Nm into v square x average divided by V. For any molecule, V square is equal to V square x plus V square y plus V square z. Because there are many molecules and because they are all moving in random directions, the average value of the squares of their velocity components are equal, so that v square x is equal to 1 upon 3 v square. Thus, equation KT5 becomes P is equal to Nm into v square average divided by 3v. The square root of v square average is a kind of average speed called the root mean square speed of the molecules and symbolized by Vrms. Its name describes it rather well. You square each speed, you find the mean of all these squared speeds, and then you take the square root of that mean, with under root of v square average is equal to Vrms. We can then write equation KT6 as P is equal to Nm v square Rms divided by 3v. This tells us how the pressure of the gas, a purely macroscopic quantity, depends on the speed of the molecules, a purely microscopic quantity. The kinetic theory of gases relates the macroscopic property of gases, for example, pressure and temperature, to the microscopic properties of gas molecules, for example, speed and kinetic energy. An ideal gas is one for which the pressure, volume, and temperature are related by the ideal gas law. The pressure of the gas, A purely macroscopic quantity depends on the speed of the molecules, a purely microscopic quantity. So friends, that is it for today. In the next lecture, we shall be discussing about what is meant by mean free path and apply the relationship between the mean free path, the diameter of the molecules, and the number of molecules per unit volume. So see you in the next lecture with more on kinetic theory of gases. Thank you very much.